Hello everyone. My name is Boldbaatar from Mongolia. So first of all, I would like to thank the organizers for the opportunity to participate in this conference. So I'm pleased to present my research work entitled Exploring Sustainable Keratin-Citric Acid Biofilm as a Eco-Friendly Solution to Plastic Bags. Presentation contained the following contains introductions, methods, resultant discussion, and conclusions. In introduction part, I will introduce the current situations of the plastic waste and ship wool in Mongolia, plus and keratin about the keratin proteins. To introduce some current situations of the plastic wastes in Mongolia. Until 2018, the production of the waste in Mongolia is increasing. So in the upper graph, we showed in the brown line shows countryside, blue line showed the capital city of Mongolia. So in total wastes, in plastic waste is the 6.3%. Ulaanbaatar city produces each year 12,000 tons of the plastic wastes. So plastic waste is not good in the environment, generally divided in two categories. This kind of wastes, including macro and micro plastic wastes. So, if directly discarded in the environment, pollute to soil, air, and water. Until degradation it takes long time in environment. So we are urgently need a biodegradable solution based on our sources. Second, I would like to discuss about the sheep. So in Mongolia, we have more than 30 million sheep. In this field, we have some problems, especially in the sheep wool. In recent years, the number of sheep has been increasing intensively for the purpose of meat productions. So due to this amount of keratin-rich organic waste is increasing, it causes an environmental problem. So now we just use the amount around the 10% of the sheep wool, and the remaining 90% is just discarded in the land environment. So keratin is the fibrous structural protein that is key component of the hair, nails, feather, horn, hoof, and the outer layer of the vertebrate's skin. So 95% of the sheep wool is the keratin. So recently, several research groups interesting to use the keratin for the production of biomaterials, including the biofilm. Because of the mechanical properties, biocompatibility, biodegradability, versatility, mechanical characteristics, also minimal immune response and environmental friendliness. So the next we want to talk about the citric acid. The citric acid is the weak organic acid. It is naturally found in the citrus fruits. This acid has several advantages to use for biofilm productions. Some groups use this acid for the gelatin agents. Also, biocompatibility, biodegradable, safe. Main function of this acid in this biofilm production is the cross-linking. So this citric acid cross-links the keratin-14, and then it makes the biofilm. So we extracted keratin using the chemical methods. Of course, there is a physical and biological methods also have. So in this method, we using the hydrogen peroxide and sodium OH for reduction of extracting for keratin from sheep wool. So after that, we checked the keratin molecular weight using the ST-spage electrophoresis. So about the biofilm productions, simply we mixed the citric acid solution with the keratin solutions. So after mixation, we homogenize it in room temperature 20 minutes, and then just cast it in the appropriate wells. So about the keratin citric acid ratio, when we mixed the keratin and citric acid were mixed in the above under mentioned ratios, including the keratin concentration was 5, 10, 15, 20%, and also citric acid concentration also same 5, 10, 15, 20%. So the liquid viscosity did not form biofilm at the low keratin content of 5%. So on the other hand, when the keratin content was the 10%, although biofilm was the formed and surface dried, the viscosity was dominant. However, when the keratin content was the highest, for example 20%, the surface was too dry and the biofilm cracked. So then, however, when the keratin content was 15, the surface of the biofilm form was uniform. As the citric acid content increased, the fluid viscosity increased. So uniform clean biofilm were formed than 15% of the keratin. Then we checked the biofilms using the scanning electron microscope. And in this result, at the ideal biofilm formation ratio, 15% keratin and 10% citric acid content. In this condition, the formed biofilm morphology was the uniform, while in highest keratin content biofilm morphology was irregular or the contained the undissolved keratins. So on the other hand, the sample with high citric acid content with less keratin content had a irregular morphology. Then we checked the FTIR error. So quantitative chemical bonds between extracted keratin, citric acid, and the mixed biofilms at the wavelength of 500 to 4000 were confirmed. So in the result, the concave of OH bond peak at the value of 3570 to 3200 of 200 of the keratin-14 was formed at the position of the amide A group. The chemical bond at 2935 to 2845 is the common peak that occurs during the linear hydrogen and carbon methylene aliphatic bonds. So, but the peak located at 1655 is the peak of the amide 1 or the carbonyl group in protein carboxyl group, and the peak of amide 2 group or amino group is the observed at the wave number of 1519. At the wavelength value of the 1219, conjugated amide 2 group was obtained. The sharp peak of the citric acid hydroxide bond and carbonyl bond and C O-bond peaks of the citric acid located at 1,389 or 1,240 to 1,174 and 1,140 mostly after the 1,000. So, however, biofilm contains citric acid and keratin peak, and the main change there, of course, is that the hydroxide bond peak at 3,294 and 3,494 of citric acid. So citric acid is no longer sharp and the absorbance is decreased. Also, sharp absorption of carbonyl group located at 1,749 and 1,700 of citric acid decreased, and absorption of amide 1 and 2 groups of keratin-14 is increased. Okay. When interacting with other biological polymers and proteins, citric acid is not only creates the hydrogen bonds but also change the macromolecular structure of the proteins. So therefore, calculations were made to determine the secondary structure of proteins on the amide 1 peak of keratin and citric acid-based biofilms. So the proportion of the protein secondary structure such as alpha helix and beta helix, coil and beta thorn is determined by the calculating the value of the 1,070, 1,700 to the 1,016 of the violet infrared spectrometer absorption results using the Gaussian distribution. So during biofilm formation, the proportion of the protein alpha helical structure increases, and the amount of alpha helical structure is highest, around 53% in the case of keratin content of 15, citric acid content of 10. The alpha and beta structures of proteins are stabilized by the hydrogen bonds between amine and carboxyl groups in polypeptide chain. Instead of the hydrogen of hydroxyl group of citric acid, the carboxyl and amino groups of natural polymers and proteins are additionally connected to form stable secondary structure of proteins. So also, as shown in the figure right, the absorption of amide 1 and 2 of biofilm mixed with chitosan citric acid becomes the sharper and increases there, which is similar to results of our research. So in the mixed biofilm of keratin and citric acid, the absorption of the hydroxyl bond of the citric acid decreases and the proportion of the protein alpha helical increases, so which is similar to the result of other biomaterials produced using the citric acid. So therefore, successful connections between keratin and citric acid indicates that formation of the biofilm due to the addition of citric acid between the carboxyl groups in the keratin polypeptide chains. The greater of the proportion of alpha helix in the protein, the stronger it becomes, the more resistant to the mechanical action and the more flexible it becomes. Then tensile strength analysis was performed using the appropriate content of the biofilm formations. For example, 15% keratin, 10% citric acid, and 15% keratin and 15% citric acid biofilms. So, and the other content was not, other biofilms was not included in the tensile strength test because it was too liquid or some biofilms are hard to break. So, as shown in table 4, the keratin and citric acid ratio of 15 and 10 biofilm show the tensile strength of the 9 megapascal and the relatively elongation break of 413%, which is very high elongations. So how the biofilm with the ratio of the keratin to citric acid of 15 can show the tensile strength of 5 megapascal and the relatively elongation at the break of 251%, which is the same high elongation, but showed lower mechanical properties than the ideal conditions. As shown in figure 16, the tensile strength of keratin and gelatin and curcumin mixed biofilm is similar to that of keratin and citric acid mixed biofilm. So, result of the biofilm tensile strength obtained by the research work are closer to the tensile strength of the polyethylene polymer used in widely used garbage plastic bags, which shows that there is a possibility of the further expanding of the research work and introducing into the productions. So next, Keratin-Citric acid mixed biofilm and citric acid thermal analysis were performed by thermogravimetric analysis. As shown in figure 18a, Keratin-Citric acid and biofilm undergo two weight losses. So keratin undergoes slight weight loss due to the moisture evaporation at 116 degrees Celsius, and maximum weight loss begins at 219 degrees Celsius. So for citric acid, the maximum weight loss occurs at 170 degrees Celsius, which is the lower melting temperature than the keratin degradations. But in the case of biofilm, most of their weight is lost starting at 220 degrees Celsius. So biofilm with high keratin content showed slightly worse heat resistance than the biofilm with high citric acid content. When keratin is mixed with citric acid, it is observed that the heat resistance of keratin decreases. As shown figure 18b, a large broad endothermic peak is observed for keratin at approximately 287 degrees Celsius. But for citric acids, there is a sharp endothermic peak at 16, 142, and 217 degrees Celsius. While for biofilm, a sharp endothermic peak is observed at 230 degrees Celsius. The peak 218 7 degrees Celsius for keratin shifted to the 237 degrees Celsius on biofilm. So it can be seen that citric acid acts as the catalyst for the thermal decompositions. So in conclusion, through this research work, we believe that we have established optimal conditions for the biofilm formations by mixing keratin protein that extracted from Mongolian sheep's wool with the citric acid. So in the future, it is believed that by improving the mechanical properties of the film, it will be introduced into production and put into use. Thank you for your attention. Have a great day. Thank you.